In a dramatic test of Fudd's fourth law, the sillier your clothes, the faster you go, riding his personal hovercraft, our own human hockey puck, the 10th anniversary man himself, Professor Clint Sprott.
Welcome to the wonders of physics. Now, this isn't really a hockey puck, but it is a hovercraft. In fact, it was powered by a cylinder of compressed air that I had on my back that forced the air out through these holes in these rubber pads on the bottom. And I show it to you because I want to use it to illustrate a principle of physics that involves motion. And in fact, when we're studying motion in physics, we often find it convenient to remove the friction. That allows us to study motion in the absence of this confusing influence. Now, we're going to be talking about a lot of areas of physics today, and beginning with motion, I would like to ask someone to volunteer to help. How about you? Come on down here. Turn around, tell us your name.
TJ Malio?
What was the name?
TJ Malio.
TJ?
TJ.
TJ. Okay, TJ. You take science in school? Face the audience here. Take science in school? Do you like it? Mm-hmm. You good at it?
Yeah.
You going to be a scientist when you get older, I hope?
Yeah.
Yeah? Really? What kind?
A marine biologist.
Marine biologist. Well, that's a good field, you know. Would you help us with a demonstration of the physics of motion?
Sure.
Okay, TJ, turn to your right. Go over to my assistant, Mr. Lovell. We're going to use TJ to illustrate a principle of physics that we call the conservation of energy. I've made here what we call a pendulum. It's a mass on the end of a long wire that is free to swing back and forth. Now, TJ, see if you can hold that right about at your forehead. And when I say I want you to let go, are you ready? Let go. Put your hands down by your side and don't move. Once more. Thank you, TJ. Now, we could be assured that this was safe because of this principle of motion that we call conservation of energy. We know the ball started with a certain amount of energy, and when it goes out and comes back, it comes back with no more than that amount. Now, we're going to talk about many of the laws of motion that were discovered over 300 years ago by a man named Isaac Newton. And we have the bust of Isaac Newton behind us to be sure we stay honest about the things we say about him. And one of his laws of motion is the law of inertia, his so-called first law of motion. And I want to illustrate the law of inertia with a beaker that contains a little bit of water. Now, if I were to pull on this cloth, what would happen? Let's try it. Well, the beaker moves. Is it going to fall? You're sure? Now, many of you have probably seen someone do that before, but you may not know that it's because of the property of inertia. The inertia of an object is the tendency that the object has to remain at rest if it's initially at rest. Now, I want to show you another example here that involves inertia. I have here a steel ball that weighs about 5 pounds. It's supported from above by a thin string. On the bottom of it are two other identical strings. Now, what do you suppose would happen if I were to pull down on this string nice and hard so that one of the strings would break? Who thinks this string would break? A few people. Who thinks this string would break? A few more, but a lot of people didn't say anything. So we should do an experiment. I'll pull down on the lower string, and we'll see which string breaks. Well, the lower string broke, as many of you thought. Now, you know, in physics and in science in general, we never like to draw a conclusion on a single experiment. We always like to repeat our experiments. So I want to do it again, and that's why I have this other string on, and we'll see if the same thing happens. This time the upper string broke. Can you see what I did differently in the two cases? What? Very, very good. The first time I gave it a quick jerk. When I did that, the inertia of the ball was such that it didn't move. And so the upper string didn't know that I had done that. And so the lower string broke. The second time I pulled very gently. And that time the tension in the upper string was the downward force I was applying plus the weight of the ball. And so that string was under more tension, and in fact it broke. So these are examples of the laws of motion, and in particular the law of inertia. Now I want to show you some things about the second law of motion. That is, when something is in motion, in order to change the way it moves, we have to exert a force. Now I have a rotating platform here that I can stand on, and if I give myself a twirl, I'll spin around. But you notice that once I start spinning, it's very hard to stop. There's really nothing I can do to stop myself. But suppose I do this with two barbells in my hands. And I'll start with them out at arm's length and bring them in close to my body. And you see, when they're far away, I go slow. When they're in close, I go fast. And that's because there's something called angular momentum that is conserved. When my moment of inertia is large, my angular velocity is small, and vice versa. Now here's another example of the same thing. How many of you have one of these? That's right, it's a bicycle wheel. Except I'll bet you don't have a bicycle wheel you can hold in your hand and spin around like that, do you? You don't see too many of those. What do you think would happen if I would get up on the rotating platform with the bicycle wheel? Let's try. Well, that's not very interesting. Suppose I put it over my head. Now the other way. So you see, I can make myself go either way. And again, that's because of the conservation of angular momentum. When the bicycle wheel spins one way, I spin the other way. And that's so that the angular momentum is always zero, in fact. They're equal and opposite, and they cancel one another. Now, the last thing I want to show you involves another way to change what I'm doing. If I'm standing on this platform, one way to make myself go around is by means of a rocket of some sort. And here I have an old fire extinguisher that makes carbon dioxide gas. And it will shoot out, and the carbon dioxide will act like a rocket, and it will make me go around. Now the question is, how do I stop? Other way. Very good. So you see, I can go either way. So that illustrates, in fact, Newton's third law of motion. Newton's third law is sometimes called the law of action and reaction. In this case, the carbon dioxide went one way, and I went the other way. Now, this law of action and reaction is familiar to you all. I have over here a gadget that I bet many of you have seen before. What is this? That's right, it's a lawn sprinkler. So in the front row, if you'll duck, I'll turn it on. Except I'm not running it with water. I'm running it with compressed air. But the idea is the same. The air goes out in one direction, and that caused the lawn sprinkler to go around in the opposite direction. And this is another example of Newton's third law of motion, action and reaction. Now, you know, there was a famous physicist called Richard Feynman that many of you have probably heard of. And when he was a student about 50 years ago, he used to go around and ask his professors and all the great scientists of the day what they thought would happen if instead of blowing the air or the water out in that direction, if one were to suck it in, make the air or the water go in the other way. Well, lots of people had opinions. Some thought it would rotate the same way. Some thought it would rotate the other way. But whatever people said, he could always convince them the other way. He had an argument for both ways, and he was very convincing. Except apparently, Richard Feynman was not completely sure himself which way it went, because one day when he was a student, he went into the cyclotron laboratory at Princeton University, and he put a lawn sprinkler like that inside of a large aquarium filled with water. And he ran an air hose out, and then he put compressed air into the aquarium so as to forced the water into the sprinkler to see which way it goes around. Well, the story has it that before he finished his experiment, he broke the aquarium and he flooded the laboratory, and he was told never to come back to that laboratory again. But in fact, we can repeat his experiment, because back here we have a vacuum pump, much like a vacuum cleaner, except it is much more powerful. And we can turn it on and actually pull air into the lawn sprinkler. How many people think it'll go around in the same way? How many think it'll go around backwards? Good. Let's try it. Would anyone like to change their opinion? In fact, air is going in. You'll have to take my word for it. There's air going in, but it doesn't turn in either direction. In fact, if you do this experiment very carefully and remove all the friction, as I did on the hovercraft when I came in, it would turn, and it would turn in the reverse direction, but very, very slowly. It would turn this way at a very low rate. And the reason is actually fairly simple, because when the air is going out, it's going out in a jet. It's all going in one direction, and that forces the lawn sprinkler to go in the opposite direction. But when the air is coming in, it's coming in from all directions. And so Newton's third law still works, but one has to be very careful how you apply it and how you understand it. So this concludes the first area of physics, which is the physics of motion. And before moving on, I want to point out to you that all of these examples of motion and all of the other examples of motion that you're familiar with, be they atoms or planets, they all move according to the laws of motion that were handed down to us 300 years ago by Isaac Newton.
I say, what's going on here? Somebody told me there was a discussion of physics taking place. Is that so?
Yes, this is the wonders of physics.
And I wasn't invited. Do you know who I am?
Why, you look like Isaac Newton.
That's because I am Isaac Newton. But that's Sir Isaac Newton to you. Sir Isaac Newton, Lucasian Chair of Mathematics at the esteemed Cambridge University. You colonists always were so, shall we say, lacking in the common social graces. But what have you been talking about today?
Well, we've been speaking about your laws of motion.
Ah, yes, my beautiful laws of motion, perhaps only to be matched by my majestic universal law of gravitation. Say, you haven't been talking to any kooky Germans by the name of Einstein, have you?
We wouldn't talk to any kooky Germans, no.
Good, good. Maybe this group has more intelligence than I first gave them credit for. All that rubbish about curved space-time and such, pure nonsense. But let's talk about some of my other inventions. There was, of course, my elegant method of fluxions, or the calculus, as you so vulgarly call it today. Have you heard of the calculus, Professor Sprott?
Yes, but I thought that was invented by that German Herr Leibniz.
Leibniz. It took him 5 years after I invented calculus to come out with his version. I heard he was taking English lessons the entire time. But did you also know that I did some original investigations into the nature of light?
Yes, I had heard that, in fact.
Marvelous. I was the first person to break the white light into a rainbow. You wouldn't happen to have such a demonstration here, would you?
In fact, we do, right over here.
Ah, marvelous.
Here I have a slide projector. Did they have those in your day?
No, I'm afraid they didn't.
Well, this one makes a beam of white light that goes through a triangular piece of glass, a prism. And up on the wall, you'll see a rainbow.
Beautiful. Just like I showed the Royal Society, except that I had the rainbow. It looks like you have a rain cup. And in any case, I used this to dispel the common myth that white light was somehow pure. And I showed that it was actually the different colors of light that were themselves pure by breaking it into the colors of the rainbow. But let's get back to talking about my laws of motion. Say, what's this device right here?
Well, in fact, I was just about to show this to the folks before you came in. This is our rocket-powered tricycle.
Rocket-powered tricycle. I must try this.
Well, now, this is very dangerous. I'm not sure we should actually let you ride it.
Oh, nonsense. Who better to control it than the person who invented the principles upon which it is based?
Well, perhaps, but you must realize we have no insurance.
That's all right. I don't know what insurance is. All right. Do you have any cranial protection for me?
Oh, cranial protection. You must mean this.
Beautiful. Now, how do I work this monstrosity?
Well, there's a grip right here that will activate the fire extinguisher on the back, and according to your third law of motion, it will propel you forward.
Let's try it.
Well, such a treat to have a visit from someone who's been dead for 300 years. But let's move on and talk about the next area of physics, which is the physics of heat. And in fact, the first demonstration of heat is very closely related to what we were just talking about with the lawn sprinkler. I have here a flask with a little bit of water in it, and underneath it is a Bunsen burner, which runs on natural gas, and I'm going to light the Bunsen burner and make a flame. Now, what do you suppose will happen as the water heats up? Somebody said the water will boil. That's right. The liquid will change into steam. Now, you notice on the top of this little flask are 4 little nozzles that come out, and they look very much like the lawn sprinkler. So what do you suppose will happen when this fills with steam? What do you think? That's a good bet. It'll spin around just like the lawn sprinkler. Now, it takes a moment for that to come to a boil, so we'll turn to something else, and then we'll come back to it in a moment. Because I want to show you another example that involves the physics of heat. And in fact, it's really the opposite of heat, which is cold. That's right. I have in this container, which is a little like a thermos bottle, a liquid. And I'm going to pour a little of it out because I want you to see what it looks like. Now, it looks a little bit like water, except you notice when it hits the table, it doesn't make things wet. And that's because this is not water, but it is liquid nitrogen. That's right. Now, you know nitrogen is normally a gas. The air you're breathing right now is about 80% nitrogen. And that doesn't look anything like this. But in fact, if you take the nitrogen in the air and cool it sufficiently, it will become a liquid. It's spinning. Very good. So we'll come back to that in a moment. The temperature you have to cool nitrogen to turn it into a liquid is 321 degrees below zero Fahrenheit, or as we prefer to say in science, 196 below zero Celsius, or even better, a mere 77 degrees above the absolute coldest that anything can possibly be. So liquid nitrogen is very cold stuff, and there are many interesting things we can do with liquid nitrogen, and I want to show you one thing that involves a familiar object. So we'll put the banana into the liquid nitrogen. You see it boils very vigorously, even though the banana is not especially hot. But in fact, compared to the liquid nitrogen, it is very hot indeed, and that's why the nitrogen is boiling. So we'll let that boil away for a moment while I call your attention over here to our little flask that's going around. Now, this was actually invented over 2,000 years ago by a man named Hero of Alexandria. These days, we would call him a theorist because he never actually built one, but he did think up the idea, and he wrote it down, and then later on, people built it. And so in his honor, it is called Hero's engine. And it looks like a very simple kind of engine. All you need is a flame, some water, and the right kind of tube, and it goes around. In fact, this wouldn't be a very good kind of engine to put in your automobile, but it is closely related to steam turbines, which are used in many applications like this. So that's Hero's engine. Now, while we're waiting for our banana to cool down, let me add a little bit more liquid nitrogen because I want to be sure that the banana is completely immersed in liquid nitrogen. Now, I want to show you something else with... Goodness. Let's stop and discuss this. How many of you have been to Yellowstone Park? Quite a few. You know, in Yellowstone Park, they have things called geysers. And this is our artificial geyser, and it works on exactly the same principle. There are many places, like in Yellowstone Park, where there are crevices that run deep down into the earth. And when it rains, water goes into those crevices. And deep underneath the earth, there are rocks that are very, very hot. Now, do you know the temperature of water boils at? Who knows? Yeah. Very good. 212 degrees Fahrenheit or 100 Celsius. Those are both good answers, except they are both wrong. That's true only at sea level. It's a good answer. But only at sea level does water boil at that temperature. If you go up on a mountain, it boils at a lower temperature. And if you go down at the bottom of the ocean or underneath a column of water like that, the pressure, like in your pressure cooker, keeps it from boiling until it gets much hotter. But of course, eventually it does boil. When it does, the pressure is relieved. Then it boils very vigorously. The water shoots up into the air. It comes into contact with the cold air, and it turns back into water, runs back down, and the heating begins again. So our artificial geyser will go off a couple of more times until I turn it off in a little while. So where were we? We were talking about liquid nitrogen. And I have here a brass cylinder. It's very heavy, very strong, inside of which is a small stainless steel cup. And what I would like to do is lower this cup down into the liquid nitrogen. Now you see that also makes the liquid nitrogen boil, and it does so because the cup is much warmer than the nitrogen. But after a moment or two, the boiling stops, and when the boiling has stopped, we know that the cup has cooled down to the very low temperature of the liquid. And that has happened now, and so I can take the cup out, and it's got a little bit of liquid nitrogen in it. If I shake it, you see, it spills. I don't want to spill too much of it, because I now want to take the cup with liquid nitrogen and lower it down into the brass cylinder. And then I will take a cork and hammer it on. And then I'll take the whole thing and shake it. You notice it blew the cork off. It went all the way up to the back row up there, and someone has a souvenir. Now, this is a good opportunity to caution you that many of the things I'm doing for you today are potentially dangerous. And so don't go home and try to repeat these things unless you do them under the supervision or with the help of someone who understands the scientific principles. It is good to experiment and to try things, but we want you to do these things safely so that you don't injure yourself. So let's see how our little banana is doing. Now, the banana is very cold at this point, and so I don't dare touch it with my fingers. It would instantly frostbite my fingers. However, I can put on these special gloves, which will protect my hand, and I will be able to take out the banana and show you that it is now quite hard. In fact, I can use it to drive a nail. Now, while we're talking about gases of various sorts, I want to show you another gas that you're familiar with. But before I do, many of you probably have blown soap bubbles before. Has everyone done that? Have some of you had one of those little pipes you put in your mouth and you blow bubbles through the pipe? Actually, we have one of those here. Here's a little pipe, but rather than put it in my mouth, I've got it connected back here to a source of gas. And I'm going to turn on the gas. Now, the particular gas that I'm using is not air, like you would use if you were blowing the bubbles with your mouth, but in fact, it is natural gas, the same kind of gas that you have in your home if you have a gas oven or a gas furnace. Now, a thing about natural gas is that it burns. And you also notice that unlike an ordinary bubble, which falls down to the ground, these bubbles rise. And that's because natural gas is lighter, or we prefer to say less dense, than air. And so the bubbles rise. And while they do, we can ignite them. And let me do that once more with the lights off, because I think it's a little prettier that way. So we'll get ourselves a nice big bubble and ignite it. Now, while we're talking about gases that rise, I have another gas over here in these balloons that rises. What do you think is in these balloons? Helium. Now, why do you think it's helium? It's rising, that's right. But I just showed you another gas here that's not helium at all, and it rises. So just because a gas is less dense than air doesn't mean it's helium. Helium is less dense than air, but there are other gases. But there is a way to tell whether this is helium or some other gas. Does someone have an idea what we might do to test it? Yeah. Someone else? Pop it. That's a good idea, except we're going to pop it using a match. Now, helium is a gas that does not burn. And so when you pop a balloon with a match that is made out of helium, it just pops. However, there are many gases, like I had over here, that in fact burn. So if we strike a match to particular gases, they will burn. And so it's a way of telling what kind of gas is in the balloons. So I'm going to light a match, put it on the end of this stick, and bring it up to the balloon. Now you notice Mr. Lovell with his fingers in his ears, and he's expecting a noise. So if loud noises bother you, you might want to do the same. We're not in Kansas. This is a physics lecture.
Physicists? They cause me no end of trouble. Why, I used to be able to fly this broom until some physicists calculated that brooms can't fly. What are you talking about to these people?
We're talking about the physics of heat.
Heat? Well, you just take some of my magic powder and put it in the palm of my hand. Good. Now, do you have a match?
Yeah?
Well, light it and put it between my fingers. No! Straight up. Yes. That's what I call heat.
Let's see if we can get through a discussion of the physics of sound. And in fact, the next thing I want to show you involves both heat and sound, because we have here a pipe that has about 200 holes on the top of it, and I'm flowing natural gas into this pipe. I'm going to light the gas with a match and make a wall of flame. Now, this is a very peculiar flame because at this end there is a speaker like you would have on your stereo set. And that speaker is connected to an amplifier and an audio oscillator that I can turn on in a moment. And when I turn it on, I want you to notice what happens to the flame. You notice the flame is large in some places and small in other places. It's no longer uniform. And as I go up to higher frequencies or pitches, notice that they get closer together. And in fact, this is an indication that sound is a wave phenomenon. And in fact, this is a measure of the wavelength of the sound. Inside that pipe is a sound wave going back and forth, and it is making the flame be high and low in various regions. Now, this is a nice indication that sound is a wave phenomenon, but it's not a very practical way to study waves in the laboratory. When we want to study waves in the laboratory, we use this instrument. What's it called? Someone said? An oscilloscope. Very good. It's a little like a television set. It has a line across that wiggles up and down, and it is wiggling in response to my voice, picked up by this microphone. And you can see how complicated the wave corresponding to human speech is. Now, there are many sounds that are much simpler than speech, and I want to show you one such example. What is this? A tuning fork, that's right. I'm going to strike the tuning fork. It will make a sound, and I want you to look at what the sound looks like on the oscilloscope. You see, it's a very regular up and down. In fact, that is a pure sound. It consists of a single frequency, and it is what we call a sine wave. Now, you know, all musical instruments have associated with them characteristic waveforms. And that's how you can tell one musical instrument from another, even if they're playing the same note. So I could take an instrument like this little recorder and play a few notes and have you look at what the waveforms look like for this particular musical instrument. Now, I'm not a musician, but I will play a note or two. So you see, it's not like a sine wave. It is more complicated. It has what in physics we call harmonics, or what musicians like to call overtones. That is to say, additional frequencies to give it the quality that it has. So this is an illustration of the waves due to various musical instruments. Now, I want to show you a very unusual musical instrument. How many have seen an instrument that looks like this? Not too many, because it is nothing more than an aluminum rod that's solid, and if I strike it on the ground, it will make a sound. So listen carefully. It makes a sound that very slowly dies away. Now, there's another way to make that sound. If I put a little bit of rosin on a rag and rub it, I can cause it to make a sound as well. You notice how long the sound lasts. And let's see what it looks like on the oscilloscope. It's actually a very pure sound, but it's very high frequency. Now, it's very important that I hold it exactly in the middle. The sound instantly goes away if I grip it somewhere else. And that's because when this rod is vibrating, its length is actually changing. It's getting longer and shorter. About several thousand times every second, it gets longer and shorter. If I hold it in the middle is not moving. The two ends are coming together, and then they're going apart. So if I hold it here, the vibration can persist. But if I hold it here, it can't move back and forth, and the sound stops. So that's a peculiar kind of a musical instrument that hopefully convinces you that sound is a form of motion. So heat and sound and motion are all closely related ideas. Now I want to show you another example that involves sound, and it also involves gases. I have back here a different kind of gas that we haven't used yet that I'm going to fill a balloon with. And I'll just tell you that this gas, as you see, is lighter than air, or as we prefer to say, it is less dense than air. And in fact, this is ordinary helium, like many of you have had before. But in fact, there's an interesting thing I can do with a helium balloon. What do you think? Breathe it? Good idea. Try breathing it and see what it does to the sound of my voice. Now, before I do this, I want to caution you. Don't go trying to breathe gases. Most gases are very injurious to you. In fact, even helium, if it's not extremely pure, can injure you if you breathe it. So don't try this. This is not a good idea unless you have very high-quality research-grade helium, as we do here. So I'm going to breathe it. Then I want you to be very quiet and listen to what it does to my voice.
And as you see, it doesn't do very much, except it makes me sound a little bit like Donald Duck.
And the reason is that sound travels about 3 times faster in helium than it does in air. And that changes the natural resonant frequencies of the cavities of my head, and it makes me sound kind of funny. Now, as I continue to talk, however, little by little, the helium will be replaced by air, and I sound more and more normal again. Now, most people have heard someone breathe helium and try to talk. How many have heard that? Just about everyone. So I would like to show you a different gas that has somewhat the opposite effect. And I'm going to fill the balloon with this gas. And I'll tell you that unlike helium, this gas is very heavy. It has a high density. And so if I were to tie it off, it would drop like a rock. In fact, this gas is something called sulfur hexafluoride. And it is another gas that it is safe to breathe, but only if it's extremely pure, as our gas is. So I'm going to breathe it, and let's see what this does to my voice.
And as you see, breathing in sulfur hexafluoride makes my voice sound very low. Now, the reason is that sound travels about half as fast in sulfur hexafluoride as it does in air. And so, it makes my voice low. Now, the other interesting thing about sulfur hexafluoride is that it's a very heavy gas, so it stays down in my lungs for a long time, unlike the helium, which rises and goes away right away. So in order to get rid of the sulfur hexafluoride, we could have my assistant, Mr. Lovell, dangle me by my feet and empty the sulfur hexafluoride out. Otherwise, I could just keep talking and keep breathing, and little by little, the air would replace the sulfur hexafluoride, and I would gradually sound normal again. At least I always have before. So let's go on and talk about the next subject, which is the physics of electricity. Now, electricity is everyone's favorite because there's so many fun things we can do with it. And I'm going to turn on a gadget over here, and I'm going to ask you where you've seen one of these before. So look carefully. Where have you seen one of those? Yes. In those balls, yeah, those plasma discharge tubes. Somewhere else, though. Another idea? Yeah. Frankenstein movies, that's right. In old science fiction movies, they often have these. And you know, there's really no practical use for these, but they are good props in science fiction movies. And it's something called a Jacob's ladder. And it works because the rods are very close together at the bottom, and there's about 20,000 volts between the rods. And that forms an electrical discharge between the rods, and then the heat of the discharge causes it to rise until the rods get so far apart that it goes out, and then it restrikes at the bottom. A little bit like the geyser. It goes over and over again. Now, that's about 20,000 volts. I'd like to show you another apparatus that makes even more voltage. It makes about 100,000 volts. And for this, it would be good if someone would volunteer. Would you come down here? Come down, turn around, tell us your name. Lindsay? Lindsay? Is that right? Lindsay, are you good at science? You have science in school, I hope, don't you? You do, huh? Would you like to be a scientist someday? Oh, you don't know. What are you going to be? Don't know yet. Well, you got lots of time to figure that out. Would you help us with an electricity demonstration, Lindsay? Okay, come right over here, and I want you to step up on this platform. Right there. Put that hand, you comfortable? Put that hand right there. Okay? You comfortable? Now just don't move your hand and you won't feel a thing. It makes a little bit of noise. Don't let that scare you. Okay? Now we're charging Lindsay up to 100,000 volts because she's connected to this dome, and there's a rubber belt that goes around and carries electric charge up to the dome. That electric charge spreads itself over her body. Some of it gets in her hair, and that causes her hair to spread apart somewhat. Lindsay, can you just shake your head? Good and hard. Now this takes a while, and the longer we wait, the more voltage she gets charged up to. The more charges we get on her hair, the more they stand up. And they do that because electrical charges of the same sign repel one another. And so her hair tries to get as far apart as it can. And this is because electric charges exert forces, much like but different from gravitational forces. Look at yourself now. You see? Shake your head again. Now look at Mr. Lovell. Shake your head. Okay, now don't move your hand, because I'm going to turn it off. Keep your hand there. And I want everyone to watch her hair. Thank you, Lindsay. Now this was safe because Lindsay was standing on this plastic stool. And it's not the high voltage that's injurious to you when you're around electricity, but it's the electric current passing through your body that's dangerous. So by having her on the stool, there was no path for the electricity to go through her body, and we could do this safely. But that's what 100,000 volts is like, and that's very dramatic. But I would like to now show you something that is even more spectacular. And for the next thing I want to show you, I need a very brave volunteer. All right, come down here. Turn around. Tell us your name.
Chris.
Chris. Chris, you look pretty brave. Are you? You ever been out in a lightning storm where there's lightning and thunder and?
Well, I've seen them. But
You've seen them, huh? Does it scare you?
Been out once or twice.
Once or twice, huh? Doesn't scare you at all?
No.
Well, you know, it probably should, because lightning can be quite dangerous.
Well, yeah, sometimes.
When you're in a lightning storm, do you stand under a tree?
No.
Very good. That's good. You shouldn't. Never be under a tree in a lightning storm.
I'll just fall down on you.
The tree might fall down, but even worse, the lightning might hit the tree, and then it would come right to your head and poof, right down through your body, and that would hurt. Not today, though. Would you help us with a demonstration?
Sure.
Okay. What I'd like you to do is turn to your right and walk right over to this cage. And have a seat in what looks very much like an electric chair. Now, what was your name? Chris. Chris, sorry. Now, over to Chris's right is a device that we call a Tesla coil. And this particular Tesla coil makes about 1 million volts. Does that scare you, Chris? A little. Aha, we're getting to him. It's not static electricity. Hang on, Chris. Thank you, Chris. Well, Chris was very, very brave to do that, and that's what 1 million volts look like. Lightning bolts are hundreds of millions of volts, or even more. They are very, very powerful indeed. Now, there are many interesting things we can do with a Tesla coil that produces 1 million volts, and the next thing I want to show you is much too dangerous to ask for any of you to volunteer. So we use one of our assistants who's worked with Tesla coils and helped us with these demonstrations for many years, and he's very skilled. And so we want to be sure that you don't try this at home. Now, one thing you probably know is that when you're working around electricity, you should not be around water. However, we have a little tray of water on the top of the stool. Now, this stool is much higher than the stool we used over here because we're now dealing with an even larger voltage, 1 million volts. Now, you notice this water has a copper rod going into it, and the copper tube goes up to the terminal of the 1 million volt Tesla coil. Now, you notice our assistant, Mark Thomas, has a crown on his head, and he has thimbles on his fingers. And that's in the event that any spark should happen to come off his body, it won't set his hair on fire. So you'll now see why we refer to Mark Thomas as the human lightning rod. Now, Mark is going to do something that I think is even more amazing. He's taken the thimbles off. To protect his hands, we're going to give him a light bulb to hold in one hand, a 500-watt light bulb. In the other hand, we're going to give him what's called a discharge tube. It has a low-pressure gas inside. It's a little like a fluorescent tube that you can see the inside of. So once again, Mark Thomas, the human lightning rod. Okay, well, these are very dramatic demonstrations involving electricity, but I now want to go on and talk about the next area of physics, which is the physics of magnetism. Now, most of you probably think magnetism and electricity don't have much to do with one another, but in fact, they are very closely related. In fact, one way to make very large magnetic fields is by means of an electric current. And I have here a coil of wire, several hundred turns, surrounding an iron core. And I can take this coil and plug it right into the wall. Now, I haven't turned it on yet, because before I turn it on, I want to take an aluminum ring and lower it down over the iron core. But before doing that, I want to point out to you that aluminum, although it is a good conductor of electricity, is not magnetic. I have here a magnet, and the aluminum is not at all attracted to it, unlike something like a nail, which is attracted to the magnet. And so it is a non-magnetic material. However, when I put it over this electromagnet and energize the electromagnet, you will see that indeed there is a force. So watch. Want to see again? The ring hops up. And that is because this magnetic field induces an electric current in the ring. This electric current is repelled by that electric current, and it jumps up in the air. Now, there's a way to actually make this work better, and that is to add a bar of iron which concentrates the magnetic field and extends it up higher. Now, when I energize the magnet, let's see what happens. Once more. Higher, someone said. Well, in fact, there is a way to make it go higher. This jumps up because it is a conductor of electricity. And there's a way to make it an even better conductor than it is at the moment. And that is to use some of this liquid nitrogen that we used before. So I'll pour some nitrogen into this dish. And you will see that the nitrogen boils. So this gives you a good chance to see what the liquid nitrogen looks like. It boils because it is much colder than the dish that it's contained in. Now, after a while, the glass will cool down to the temperature of the liquid nitrogen, as will the aluminum ring. Now, the electrical properties of materials change when they get cold. In fact, aluminum becomes about a 7 times better conductor of electricity at the temperature of liquid nitrogen as it is at the temperature of the room. And so, once it's cooled down, we will know that it is cold as the liquid nitrogen once the boiling stops. And so the boiling is now stopped, and we have a ring at the very low temperature of the liquid nitrogen. So let's now put it over the iron core and try again. Wait a minute. Would you like to see that once more? Do what? I'll try anything once. Okay. So that is an example of inducing electric currents in electrical conductors. Did you have a question?
Yes, is that the theory of superconductivity?
It is related to superconductivity, but this is not a superconductor. There are materials that are superconducting at this temperature, but not aluminum. Okay. Now, the next thing I'd like to show you is very closely related to what I just showed you, and that makes use of another aluminum object. An aluminum soft drink can, also not at all attracted to the magnet, but it is a good electrical conductor. And I can lower it down into this coil that has about 5 turns of copper tubing, and the coil is connected to a device that we call a capacitor. Now, a capacitor is like a storage battery. We can charge it up to a very high voltage, and you can see that by this meter on the front. It's coming up to about 4,000 volts. When it gets up to about 6,000 volts, we're going to discharge the capacitor into the coil and make a very large magnetic field and see what it does to the can. Now, you notice my gun-shy assistant, Mr. Lovell, with his fingers in his ears, and you may want to do the same if loud noises bother you. So is everyone ready? Here we go. Look what it did to the can. Now that went pretty fast. Would you like to see it again? Okay, except this time with one slight difference. Do you play baseball? Put that glove on if you would. Thank you. Well, we have here a replica of a device that was invented about 200 years ago during the French Revolution by a doctor named Joseph Guillotine. He used it for an application somewhat different from what we're going to show you today. But this device has a very heavy copper blade. Now, copper is another material that is a good electrical conductor, but it's not at all attracted to a magnet. Now, we're going to raise the blade. Look what it did. Now, so far, we haven't illustrated very much physics, and so we're going to repeat this, as we like to do in physics, with one difference. There are a number of very powerful magnets that are right next to the copper. Now, remember, copper is not normally attracted to a magnet, but in this case, the copper will move by the magnet so fast that an electric current will be induced in the copper, and that will exert a force on the copper, much as we exerted forces in the other examples. Okay, well, those are examples of magnetism. The last area of physics that I would like to talk about today is the physics of light. Now, you've already seen one example of light. When Isaac Newton was here, he showed you that white light was made up of all of the colors of the rainbow. I'd like to show you another source of light that, in fact, is not white, but it has a kind of a bluish-green color. Do you see the dot on the wall over there? That dot is produced by what we call a laser. And a laser produces a very fine beam of very intense light of a single frequency. And this laser beam is coming across the room here. And if I hold my hand here, you can actually see the laser beam on my hand. Now, it's hard to see the laser beam in between the room here. And so, in order to make it more visible, I can take some erasers and make some chalk dust. And when the laser beam scatters off the fine particles of chalk dust, you'll be able to see it if I turn off the lights. And you notice the light travels in a perfectly straight line. In fact, it doesn't travel in an exactly straight line. Light actually bends. In fact, light falls. Just like you were to throw a rock, light is affected by gravity, but only by the tiniest amount. And it would be very hard to do an experiment to convince you of that, but it has been done, and we now know that light is affected by gravity. There's another way that we can make light bend, and I have an example of that here. It's a plastic tube, and we're going to shine the laser into one end of the tube and turn out the lights and let you see how the laser beam travels around inside the tube. It reflects off the inner walls of the tube and goes round and round and eventually comes out the other side. Now, this device, quite appropriately, is called a light guide. It guides the light from one place to another. And in fact, light guides have very important applications. One can make light guides that you can bend. This is a light guide made of many, many very fine threads of glass. Like the hair on your head, they're so fine. When you make glass that fine, you can actually bend it. As long as you don't bend too much, it won't break. And you can shine the light in one end, and it will come out the other end. One can make this even finer. Here are some other examples of flexible light guides. And this is what we call fiber optics. And you know, someday this will revolutionize society, because in 5 to 10 years, every one of your homes will probably have a fiber optic cable of this sort coming in, bringing telephone, television, and computer data, and you'll have access to all the libraries of the world by information that travels on a beam of light in a fiber optic light guide. I would like to conclude the show in the same way that we have concluded every single one of the 85 shows that preceded this one, and that is by making a cloud. So I'll put on my top hat. We'll bring out a tank of liquid nitrogen into which we force nitrogen gas, causing the nitrogen to boil, comes out through the top, cools the air, and condenses the water vapor out of the air into liquid water, very tiny droplets that we call a cloud. So thank you all for coming.